The theory that explains everything from the simple force of a thrown pebble to the bizarre, invisible interactions of electrons. That theory is quantum field theory. We will talk about why it is called the most beautiful theory. To do that, we need to deep dive into the past to understand the full grasp of it. Let's go back to the 17th century. Classical physics is king. It's not just a subject, it's pure magic. Newton's laws of gravitation and motion gave humanity a kind of superpower. You could throw a pebble from a building and calculate its exact height. You could fire a cannonball and know precisely where and when it would land. But it went deeper than that, much deeper. Using the mathematics of Newton's laws, an astronomer named Urbain Le Verrier was studying the orbit of Uranus, and he realized something was wrong. The numbers didn't add up. The planet wasn't moving the way it should. His conclusion? Something massive, something invisible was tugging on it. Based purely on the math of classical physics, he predicted the existence and the location of a new planet. That planet was Neptune. Think about that. Classical physics discovered a world without ever seeing it. And that's just one branch, the study of motion. Classical physics also had thermodynamics for heat, optics for light, acoustics for sound. It even had a complete and accurate explanation for electricity, magnetism, and electromagnetism. It seemed to have an answer for every single phenomenon in the natural world. It was, without a doubt, the most beautiful theory in existence. Then came the 19th century, and one single glaring mistake made it lose that crown in the blink of an eye. What was that mistake? It had to do with a light bulb. Classical physics made a startling claim that when you turn on a light bulb, it emits an infinite amount of ultraviolet rays. Now let that sink in. If that were true, the sheer amount of harmful radiation would have killed us all. But that's not happening. So what was going on? Was classical physics wrong? Or did it know something we were missing? The issue stemmed from an observation. Scientists noticed that bulbs emit different colors of light at different temperatures. Orange at 1000 Kelvin, yellow at 5000 Kelvin, blue at 10,000 Kelvin. They plotted this on a graph, and all the brilliant minds of classical physics came together and gave us an explanation. The Rayleigh-Jeans law. This law had an equation that worked perfectly at lower temperatures. It predicted the graph beautifully, but when they plugged in higher temperatures, like 5000 Kelvin, the temperature of the surface of the sun, the graph didn't turn back down as it did in reality. Instead, it shot straight up to infinity. According to the math, any object at 5000 Kelvin or more should be releasing an infinite amount of UV energy. But that's impossible. The sun is vast, but its energy is finite. Classical physics had hit a wall. This was known as the Ultraviolet Catastrophe. And it was a catastrophe indeed. Enter the master, Max Planck. He looked at this problem and made one tiny, almost humble assumption. He proposed that energy doesn't flow in a smooth, continuous stream like a movie. Instead, it flows in tiny, individual frames, in discrete packets, little bundles of energy he called quanta. The size of each individual packet? A number so small it's almost abstract. 6.6 times 10 to the power of negative 34 joules, the Planck constant. And when he took this constant and inserted it into the failed Rayleigh-Jeans law, something magical happened. The graph changed. The line that was shooting off to infinity suddenly curved back down. It now matched the observed real-world data perfectly. With this one move, classical physics was back on top. The crown was secure. But you know what they say, what goes up must come down. Classical physics soon gave another explanation so illogical that it was the beginning of the end. It was about the atom. According to classical physics, any charged particle, like an electron, that is accelerating must radiate away its energy. So an electron orbiting a proton should be constantly losing energy. It should spiral inward, crash into the nucleus, and the atom should collapse instantly. But it doesn't. And if it did, you, me, this entire universe, we wouldn't exist. At the same time, scientists became utterly fascinated by Planck's constant. They started to think, we've been looking at the world on our scale, the macro scale. But what if the true, more accurate explanation for everything is happening at the microscopic level? And so they started poking and prodding the atom. This was the birth of a whole new beast, quantum mechanics. Its fundamental idea was that electrons can only exist in specific, discrete energy levels. They can't spiral inward continuously. This explained the stable atom. And with that, all the greats, Einstein, Heisenberg, Schrödinger, jumped in and turned quantum mechanics into the most beautiful theory of the 20th century. It was talking about subatomic particles, multiple universes. It was wild. But then it too started to unravel. It gave two explanations that bordered on the absurd. First, quantum entanglement. We know that two entangled particles, no matter how far apart, are linked. Measure one, and you instantly know the state of the other. The problem? That instantly seemed to be faster than light. But Einstein's special relativity, which was rock solid, stated that nothing, not even information, can travel faster than light. So, how did quantum mechanics explain it? It came up with something called retro-causality. It suggested that the moment you measure particle A, particle B effectively travels back in time to the moment of entanglement to coordinate their states. Let me say that again. Future events trigger past events. I send you a text, and you received it yesterday. It's mind-bending. The second failure was beta decay. In this process, a neutron turns into a proton and spits out an electron and an antineutrino. The entire process, including the very formation of these new particles, happens, you guessed it, faster than light. And quantum mechanics had no good explanation for this. There was a void, a gaping hole in our understanding of reality. And into that void stepped quantum field theory. This theory changed the entire game. It proposed a breathtaking idea. According to the standard model, every single type of fundamental particle has its own field. And these fields are everywhere. They permeate the entire universe. They are all stacked on top of each other, filling all of space. So, what is a particle? A particle is just a localized vibration, an excitation in its respective field. An electron is a little knot of energy in the electron field. A quark is a ripple in the quark field. Now, let's look back at beta decay with this new lens. How does QFT explain it? It says that in beta decay, energy is instantly transferred from the down quark field to the up quark field. This energy then transfers through the W boson field, which is the field for the weak nuclear force, and finally, that energy excites the electron and neutrino fields, creating the electron and the antineutrino. No faster than light travel needed. The energy was just moving between fields that are already everywhere. Do you see the profound beauty in that? It means the electron in the screen you're looking at right now, the electron in your body, and an electron in a galaxy a billion light years away, they are all exactly the same. Because they are all just excitations of the one single universal electron field that spans all of reality. It's a picture of a universe woven together by an invisible, vibrant tapestry of fields. A theory that finally reconciled the weirdness of the quantum with the rules of relativity. A theory that didn't just patch the holes, but redefined the very fabric of what things are. That is why it alone gets the title. That is why quantum field theory is, to date, the most beautiful theory in the world. What do you guys think? Let me know in the comments. And as always, don't forget to like and subscribe to Brainwave. Until the next time, take care.